Hello everyone and welcome back. Today we'll be talking about fluids. Mainly speaking, we'll be talking about contact angle and also capillary rise. So these two topics are actually interconnected, so I thought I would do one single video on them. So conventionally speaking, contact angle is defined as the angle between the tangent to a solid surface. This is supposed to be straight, but I can't get it to be straight. Yeah, the tangent to the solid surface. Assume that this tangent that I've drawn here is a solid surface, and I'm going to place a liquid droplet over here, alright? So that I'll allow that droplet to get a shape somewhat like this, okay? Alright? So the contact angle is the angle between this tangent and the tangent to the surface over here, which is somewhat like this, I guess. Yeah. So the angle would be this angle over here, theta. Alright, so this is well and good, but what does it actually mean, and why does the liquid actually bend like this near a solid surface? So to understand that, we'll actually need to look at cohesive forces and adhesive forces. Now, adhesive forces are mainly the forces that act between two different types of materials, that is between solids and liquids, and mainly between solids and liquids. So suppose I have a liquid over here and this is a solid container. So there would be an adhesive force between this liquid over here and this solid over here. So between different materials, just gonna write, I should write in the short form, but yeah, diff materials and okay, yeah, fine. And cohesive forces, alright, they act between the same types of materials. So there are cohesive forces between gases, between the same gas. Then there are cohesive forces between molecules of the same liquid. So all throughout in this liquid over here, there are cohesive forces between different molecules. Alright, so I can say over here between the same material, molecules of same material, molecules of same material. And the magnitude of these adhesive and cohesive forces depends on the nature of the material. That is, the value of the cohesive force will most likely depend on the nature of intermolecular attractions between the molecules. That is, if there are hydrogen bonds between them, or if there are dipole-induced dipole forces, and so on and so forth. So the magnitude depends on the nature of the fluid or the material that we're talking about. So, and another thing to note, so let's actually begin analyzing these two situations to see why and how the liquid bends. Now, the adhesive force over here will always be perpendicular to the surface, alright? This adhesive force will always be perpendicular to the surface. So let's write, say, F and A to denote the adhesive force. Now, at this very point over here, the cohesive forces over here will actually be the surface tension of the liquid, yeah? And the surface tension will always be pointing in, to be trying to minimize the surface area, right? So it'll actually be pointing along the tangent to the surface, okay? So it'll be pointing somewhat over here. So that over here is the cohesive force, okay? And there is of course also the weight of the fluid. So that's going to be acting directly downwards, obviously. So we can denote this by, say, W. So in order for a liquid to remain at equilibrium, we know that the net force has to be perpendicular to the liquid. If the net force is not perpendicular to the liquid, then the liquid can move either to the left or to the right, and then it would not be in equilibrium. So in order for it to be in equilibrium, the net force has to be perpendicular to the fluid. So we can write F net is along this direction, somewhat along this direction. So I'm just going to write F and denote this by net. So in order for the net force to be in this direction, the liquid must be shaped just exactly like this. It must have a concave surface, so to say. So in order for the net force to be like this, the surface of the liquid actually has to bend like this, like the concave shape that you see over here. That's why the liquid bends like this when there is like a cohesive or adhesive force between the surfaces. And of course, the contact angle over here is around theta over here, so it's a very small value. Alright, so in the case of this fluid over here, you can probably see that it has a much higher contact angle, something that is close to around 180 degree. So for this fluid, it can be explained by the same process, but the direction of the forces will be different here. So in the case of the cohesive force, which here is the surface tension actually, is actually acting towards up here because there are molecules over here as well. So they are pulling there are actually a greater number of molecules over here, so they are pulling the liquid surface in this direction. So this is going to be Fc, alright. Now there's also the adhesive force that acts perpendicular to the surface over here. That will remain Fa. Adhesive force, that magnitude, the value of magnitude of that force does not change because it is the same material. And of course there's also the weight of the fluid down here. Okay, so again, then when you add these forces vectorially or through superposition principle, what you'll actually get is a net force that acts somewhat in this direction. So in order for this liquid surface to be perpendicular to the net force, it bends in this direction so as to give sort of a concave surface, and the contact angle is much higher, it's around theta. So you could say that there is somewhat a relation between contact angle and the values of these adhesive and cohesive forces. So I guess you could write theta is directly proportional to Fc by Fa. That is, the greater the cohesive force, there's most likely a greater contact angle, and lesser the cohesive force, there's by ratio, the lesser the ratio of the cohesive force and the adhesive force, lesser is the contact angle over here. So having got that cleared up, we'll actually now move on to looking at how capillary rise actually occurs in a fluid. So that I'll move on to the new page over here. So let's begin with that. Also note that this is not a strict mathematical relation. This is merely something that I wrote to help you get a better idea of how the contact angle varies with the magnitudes of the cohesive force and the adhesive force. So just something to note there. Alright, so let's begin with actually describing what capillary rise actually is. I mean, I've used it frequently throughout the video, but I've not actually explained what it is once, not even once. So, capillary rise is a phenomenon in which the liquid placed in a narrow tube of, say, you could say a radius r, okay, of radius r, it rises to a height h due to the differences in adhesive and cohesive forces of the fluid that mainly depends on the contact angle, which we just discussed in like a few minutes ago. So that's why capillary rise happens, and depending on the contact angle, the liquid could be above the surface of the fluid over here, so above the surface of the rest of the liquid, or it could be at the same height, or it could even be depressed further down below. So it could be somewhere over like that. But here we're going to discuss the case in which the liquid actually goes above the water, in which, and this is the case in which the contact angle is actually between 0 and 90 degree. So we could say theta, and this is 90 degree, or pi by 2. So let's actually begin. Alright, so what we're going to consider is we're going to talk about the forces that act on the entire part of the liquid that is raised above the water level. So just to like reduce the confusion, I'm going to remove that part there. So what we're talking about here is the force of gravity that's acting on this entire part that is raised above the water. So that's going to act approximately somewhere over there. Okay, I don't know why this pointer keeps messing up. So we're going to write that as say mg for now. Okay, then we're going to talk about the force of surface tension that acts on the fluid. Alright, we know that the force of surface tension along these lines along at the edges will act inwards as we discussed earlier, but what we actually care about here is the forces that are acting on the liquid from outside forces, that is the so the surface of the capillary tube to be specific. So all the adhesive forces will actually cancel out because they're acting perpendicular to the surface. So what we actually care about is the reaction force of the surface tension that will act on the fluid at these edges over here. So how you can imagine it as is that there is some force of surface tension acting over here that wants to pull the liquid molecules in, and then there's a reaction force that actually wants to keep the molecules on the surface, and this force is actually exerted by the surface. So we'll say that this force has a magnitude equal. Alright, so if I denote the coefficient of surface tension as T, so we'll say that this force for this minute length over here has a magnitude T dl. Okay, so what we consider next is the contact angle that is there, right? So we can see that the tangent to the liquid surface is somewhere along this. So we can say that if I extend a line over here, that's supposed to be a line. This will be theta, and thus this angle over here will be theta as well. Okay. So now if we'll actually look at it closely, if you take the the sine theta component of this value, you'll get a force that is again perpendicular to the surface over here. So I'm just going to denote this over here, and I'm going, oh god, it's not straight. Hold on. So I'm going to draw it like this, and I'm going to write still not straight, T dl sine theta. Now again, since this is actually perpendicular to the surface, so if we consider completely around if you go around the capillary tube once, all the TDL sin theta components will actually cancel out, because there'll also be a TDL sin theta component over there, and there'll be a TDL sin theta component behind this tube, and like towards this tube, towards us and behind us. So like all of these components will actually cancel each other out, and what you'll end up with is just TDL cos theta component over here, right? So I'm just going to draw a TDL cos theta component over here. Alright, so what the conclusion that we actually come to over here is the TDL cos theta component is actually responsible for raising this value of, or raising this mass of water above this water level. So that's where the contact angle actually comes into play, because if cos theta is below above 90 degrees, this cos theta value will actually be negative, and hence the liquid will actually go below the surface. And similarly, you can make different conclusions based on that. Also, the analysis, like if you're still not satisfied with this, you can also think of it in some other way. So we know that the pressure at this point has to be equal to P atm, alright, and the pressure at this point has to also be equal to P atm. So from Pascal's law, we also know that the pressure at this point has to be equal to P atm. But how can that be possible? Because we do have some fluid above this at a height h that actually exerts pressure on it, right? So the reason for that is that the pressure that this fluid exerts is nullified, because this force of surface tension actually lifts the liquid up. So that's just looking at it qualitatively. So now we'll actually try to derive the value of the height h that this fluid rises to. So what we're going to do is, first we'll try to evaluate the total force that acts on all surface molecules. If you can imagine it, it's actually a ring, right? It's actually a circle that this edge forms. This meniscus, that is this shape that is formed here, is called the meniscus. This meniscus actually goes all around the capillary tube. So what we're going to do is, in order to find the total force, we're going to say F is equal to integral, oh god, so that's supposed to be an integral 2 pi r f dl cos theta. T dl cos theta, hold on. So, just like that, yeah. So it's going to be T dl cos theta. Now T cos theta is actually a constant, so we can just write this as T into 2 pi r, where r is the radius of the meniscus tube, into cos theta. So we can denote T over here to denote the fact this is actually surface tension. So Ft is equal to T into 2 pi r into cos theta. And now what we can actually do is we can equate this to the force that gravity exerts on this mass of water over here. So what you're going to do is Ft is equal to Fg, alright, and we can also say T into 2 pi r cos theta is equal to mg. But we can actually further simplify this if we actually include a value for m in terms of rho and v. So now we can, that we can write m as rho v. So are we actually going to do that? So T into 2 pi r, hold on, into cos theta is equal to rho v, that is rho of water or any fluid. We can just say fluid over here. Rho fluid, then volume of the fluid that has been raised into g. So now volume, actually we can, although this isn't a cylinder right here because the surface over here or the top actually is curved, we can approximately write this volume as pi r square h. We can approximate it as a cylinder. It's not entirely correct. If you really want very accurate values, you can write pi r square h minus the volume of the hemisphere that will be formed when theta is actually equal to 0. So you can do that if you'd like, but it's just convenient to write pi r square h to get a very nice expression, as you'll see. So T into 2 pi r cos theta is equal to rho into pi r square h. Now this is h is what you're trying to isolate here, right? So we finally got h over here. So we can cut pi and pi over here. We can cut an r and an r over here. And so what we'll actually get is h is equal to 2t cos theta by rho g and r, rho gr. That is the radius of the capillary tube. So this is actually the expression for the capillary rise that occurs when a capillary tube is thrust or pushed into a liquid with which it has a contact angle between theta and between 0 and 180 degree. So if, as I told earlier, if theta is actually below uh, below 90 and above 0 degree, they will actually rise in the tube, and if it is above 90 and below 180, it will actually go down in the tube, and the value of the contact angle just depends on what we discussed earlier in the video. So this is how you describe capillary rise quantitatively, and I hope you enjoy the video. So thanks for watching.